Welcome to Lecture Online, and now we're going to see how difficult it can be to determine the luminosity of a star. Now, what does that mean? What does luminosity mean? Well, it's kind of like brightness, but not quite. When we look at a star and we say, wow, look how bright it looks, we're not just talking about luminosity, we're talking about how much light it puts out, how much visible light it puts out. And luminosity is really a measurement of how much total energy the star puts out. And notice that the star typically, or any star typically, will put out energy in UV, visible light, and infrared radiation. So when we talk about the brightness of the star, we typically are talking about how much visible light it puts out and how bright it looks towards us. Now we have, of course, apparent brightness. How bright does it appear to us? Because a very dim star that's really close to us will look very bright, and a very bright star that's very far from us will look very dim. So when we talk about brightness, we typically talk about the visible light portion of the emission, electromagnetic emission of a star. A star can also put out UV and infrared, and for some of the very bright bluish stars, most of the energy a star puts out is in the UV, and only a small amount comes out in the visible light and infrared. So when we talk about luminosity, we talk about all of the energy, all three of the bands, UV, visible, and infrared radiation, that the star puts out. So how do we determine the luminosity? You can see that simply looking at it or measuring it with a light meter is not sufficient, because it will not pick up all of the radiation coming from the star. We need to pull out all of the radiation. Another big problem that we have with trying to find the luminosity of stars is understanding the difference between the absolute luminosity and the apparent luminosity. In other words, the star may appear luminous, but we need to figure out how far the star is from us before we actually can determine how luminous it actually is. What is the actual luminosity of the star? How much energy does it put out? And again, that can be very difficult to determine. But we did find out a mass-luminosity relationship. We do know that the luminosity of a star often has to do with how much mass it has, especially when we talk about a main sequence star. On the main sequence star, we realize that if we determine where on the main sequence a star appears, we can then determine how much mass it has, and from that we should be able to find a mass-luminosity relationship. Notice that the general relationship is that the luminosity of a star relative to the luminosity of the sun, if it's brighter, it's bigger than 1, if it's not as bright, it's less than 1, is equal to some constant times the ratio of the mass of the star divided by the mass of the sun, and that quantity to some exponent. And then we realize that that relationship varies depending upon how much mass the star has. And we've been able to classify it in 4 different equations depending upon the mass. We have an equation if the mass of the star is greater than 20 times the mass of the sun. We have an equation that's different when the star has a mass between 2 and 20 times the mass of the sun. We have another equation when the mass of the star is between 0.43 and 2 times the mass of the sun. And then finally we have a 4th equation when the mass is less than 0.43 times the mass of the sun. And remember, of course, that there's no star that can have less than 0.08, so 0.08 times the mass of the sun is the smallest main sequence star that can exist. Any star smaller than that will not produce enough pressure at the center of the star to get the temperature up to 10 million degrees Kelvin to get nuclear fusion started, and then it becomes what we call a failed star or a brown dwarf where no nuclear fusion takes place. So in the case when the mass of the star is less than 0.43 times the mass of the sun, of course, and greater than 0.08 times the mass of the sun, the equation is that the ratio of the luminosity is equal to the ratio of the mass raised to the 2.3 power. Then we can see that the mass-luminosity relationship changes. There's a different slope to the curve, and therefore between 0.43 times the mass of the sun and 2 times the mass of the sun, so stars that are fairly similar to the sun, the equation becomes the relationship between the luminosity is about equal to the relationship of the mass to the 4th power. Then when we talk about the bigger stars bigger than Vegas and Sirius, which are now in the range from 2 to 20 times the mass of the sun, the relationship changes to the ratio of the luminosity of the star to the luminosity of the sun is about equal to 1.5 times the ratio of the masses to the 3.5 power. And finally, for any stars greater than 20 times the mass of the sun, which is a very rare type of star, there's not very many stars with that kind of mass, it's simply 3,200 times the ratio of the mass of the star divided by the mass of the sun, and that gives you the luminosity relationship. Now what I've done is I've gone ahead and calculated it for the limiting cases. So we can see that going from 0.08 to 0.43 times the mass of the sun, that means that the luminosity is less than 1/1000 the luminosity of the sun to about 1/3 the luminosity of the sun within that range. For stars from 0.43 times the mass of the sun to 2 times the mass of the sun, the luminosity ranges for about 1/3 to about 16 times the luminosity of the sun. For stars from 2 times the mass of the sun to 20 times the mass of the sun, the luminosity is about from 17 to 54,000 times the luminosity of the sun. Imagine 54,000 times as much luminosity of the sun. And then for stars that are more than 20 times the size of the sun, it would then be greater than 64,000. Notice there's a little bit of a mismatch here between the two equations. There's kind of a jump, which is of course not normally the case, but the equations don't quite mesh at this particular limit. But you can see anywhere from 50 to 60,000 times the mass of the sun by the time the star is about 20 times the mass of the sun. Notice that this is only for main sequence stars. When we have stars that are like giants, that are much larger in size relative to their mass, they may have greater luminosity relative to their mass, and that relationship then of course doesn't work. We have to work with different kinds of ways to determine the luminosity. But this is kind of nice because we have now ways using filters and using various ways to determine where exactly the star belongs on the main sequence based upon the spectral type and the spectral lines and the light coming through various UVB filters. We can place it on the main sequence fairly accurately, and then we can have a fairly good representation of what the mass of that star has to be, and then based upon that and using these equations we can get fairly close to that luminosity of that star. And even though it's not exactly an exact science, so to speak, although this is science, but what I'm trying to say is that the number you get will have a fair amount of uncertainty in it, but it gives us at least some ballpark range of what the luminosity of the stars is by using these techniques. So again, in astronomy, it's always a struggle to find accurate numbers of anything, and the more ways we have to measure the same thing, the closer we can actually get to the actual value, and in this case, the determination of what the luminosity of stars is. So this is a really good start. This at least gives you an idea of what the mass luminosity relationship is and how we calculate it for various stars with various masses on the main sequence. And that's how we do that. Welcome to L&R&M, and now let's look at some examples for stars and their relative luminosities relative to the sun, and that helps us understand what we mean by luminosity. So we have a set of stars right here on the list, starting out with Sirius B. Sirius B is a white dwarf, very small star, has a very high surface temperature, but a very small radius. Corresponding the luminosity relative to the sun, it's 0.025 times the luminosity of the sun, or 2.5% the luminosity of the sun. Here we have Barnard star. It's about 6 light years away from us. It's an M4-5 star. That means it's spectral class M, type 4, and luminosity class 5, which means it's a main sequence star, but this looks like it's a small red star. Surface temperature, 3250 Kelvin. The radius is about 2/10 the radius of the sun, and therefore luminosity is less than 1%, about 0.5% the luminosity of the sun. Now notice these numbers, of course, are estimates based upon measurements that were made, and depending upon where you go for sources, you'll see different numbers for some of these as far as temperature, size, and so forth. So don't take these as being the absolute correct numbers. They're the best numbers that certain scientists came up with as they made certain measurements, but as time goes by and we get better telescopes and better measuring apparatus, we will get better and more accurate numbers for these. Remember, this is not an exact those are not exact numbers. It's very difficult sometimes to come up with some of these. For example, Sirius A and Vega, those are very close in the type of stars that they are. Notice there's an A15 and an A05, so they're both main sequence stars. They're fairly warm on the surface, very hot. They're whitish looking stars. Notice that Vega should be hotter than Sirius, but nevertheless, the numbers that we got is it looks like Sirius has a hotter surface temperature than Vega. Part of that is because the radii are different. Notice that Sirius is a smaller, more dense star, then Vega is a larger star, and therefore the luminosity is much greater for Vega as it is for Sirius. Even though the surface temperature is greater for Sirius, Vega is a larger star. Now we have Arcturus, which is the largest star in the constellation Taurus. It's a K 1.53 star, meaning it's a K-class star, but it's not a main sequence star. It's a red giant, so therefore they're much bigger in size. Surface temperature a little bit lower, 4,500 Kelvin. 21 times the radius of the sun. Correspondingly, the luminosity is 160 times the luminosity of the sun. Okay, Regal is that very bright bluish looking star in the constellation Orion. Notice it's a B8 but a 1A star, so it's a very luminous giant star. It's bluish in color, very hot surface temperature, 11,000 Kelvin, 70 times the radius of the sun. Notice the luminosity is 63,000 times the luminosity of the sun. One star putting out as much energy and light as 63,000 sun-like stars. Aldebaran, which is a star that's pretty close to Orion, K53. So here we have, again, a red giant. K5 meaning it's a lower surface temperature. I didn't get the radius on that star, and the luminosity for that one red giant is 370 times the luminosity of the sun. Deneb is a very bright star. It's an A2 1A. 1A means it's a very luminous giant. A2 means it has very high surface temperature, about 8,500 Kelvin. It is an enormous star in size. It's 203 times the radius of the sun, and therefore a luminosity of about 200,000 times the luminosity of the sun. And just to give you an example of how difficult it is sometimes to get good measurements, Betelgeuse is a very difficult star to measure. We're still not quite sure what the distance is to Betelgeuse. We're not quite sure what the size of Betelgeuse is, what the surface temperature is for Betelgeuse, and therefore you can see that we don't have very accurate measurements for the size since we don't know the distance to the star, and so therefore the luminosity varies anywhere from 36,000 times to 100,000 times the luminosity of the sun, depending upon which numbers you want to pick and what combination of temperature, size, distance, and so forth you want to grab. Again, Betelgeuse is an M1 star, so it's a red star, not very high surface temperatures, but it's a 1AB star, meaning it's a very luminous supergiant. That's why it's so luminous compared to the luminosity of the sun. All right, so that gives you kind of a feel of how we come up with the luminosity. It's always based upon surface temperature and size combined gives you the luminosity relative to the sun. And that's how we do that. Welcome to Electron Line. Another way in which we can determine the luminosity of a star is using the Cepheid-Boltzmann law. The Cepheid-Boltzmann law determines the power output, the energy output of any object based upon the radiation. Stars radiate energy, and the equation is equal to the emissivity times the Boltzmann's constants times the surface area of the object times the temperature of the object to the fourth power. Of course, the temperature must be in Kelvin. The emissivity of an object depends, of course, on the material, but for stars, the emissivity usually is number 1. So emissivity goes between 0 and 1, so that means just all of the energy that it puts out in the form of radiation. And the constant, the Boltzmann's constant, was experimentally determined to be 5.67 times 10 to the minus 8 watts per square meter per Kelvin to the fourth power. So the units come out to be watts. Now, notice the surface area of a sphere is equal to 4 pi r squared. And since E is equal to 1, we can just go ahead and leave it out. So L is equal to this. That means that if we compare that to the luminosity of the sun, we could say that the luminosity of the star divided by the luminosity of the sun is equal to the ratio of the ratio squared times the ratio of the temperature to the fourth power. That's where this and that comes from. So we can actually do that in terms of how luminous is it relative to the sun. We can come up with absolute numbers by putting in the actual radius in meters and the actual temperature in Kelvin. Using the constant here, we can actually find the actual output of the sun or output of any star. For example, the luminosity of the sun is 3.9 times 10 to the 26 watts. And that's how much energy the sun puts out on a second-to-second basis. But we can go ahead and find the luminosity of any star as long as we know the radius and the temperature of the star. Now again, you know that finding the radius and finding the temperature of the star is not exactly as easy as it looks, but we can get reasonably close. And for example, Regal, the radius is about 70 times the radius of the sun, and the temperature is about 11,000 degrees Kelvin. So relative to the sun, what is the luminosity of Regal? So let's go ahead and work that out. So the ratio of the luminosity divided by the luminosity of the sun is equal to the ratio of the radii. So the ratio would be 70 to 1, 70 to 1, quantity squared, and the temperature for Rigel is 11,000, and the temperature for the Sun is about 5,800. It's actually slightly less, 5,770 or something like that, but that's close enough, and we raise that to the 4th power. So now we need a calculator. So we take 11,000, divide by 5,800. We raise that to the 4th power, and then we multiply that times 70 squared equals, and we get 63,400. So that's about 63,000, so that would be 63,400, which means that the luminosity of Rigel is about 63,400 times the luminosity of the Sun. And so simply by knowing the radius and the temperature, we can figure that out. Now, it turns out when it comes to stars, figuring out the temperature is probably the easier one of the two to do. Figuring out the radius is more difficult, because how do you figure out the radius of a star? Well, there are ways we can do that, and we'll show you that in some future videos. But anyway, if we can get both, then we can figure out the luminosity. Sometimes we can actually use this equation by figuring out what the radius of a star is by knowing the luminosity and the temperature, because there's other ways in which we can find the luminosity, especially using the mass-luminosity relationship. We can find the luminosity in a different way. The temperature by using filters and by using the spectral class, and by using Wien's law, we can usually find the temperature of a star, we can find the luminosity of a star, and then we can double back and find out the radius of the star using this very same equation. So depending upon how we can measure things and what we can measure about a star, we can slowly zoom in and get all the different specifics about the properties of a star using this kind of equation. That's how we do that. Welcome to Lecture Online, and now we're going to take a look at determining stellar radii, determining the size of stars, the physical size of stars. And of course, in the universe, when we measure things, we tend to measure things in terms of the angular size. How big does it look? Like the moon is about 1/2 degree in angular size. If you measure the moon from the top to the bottom, it makes up 1/2 degree. If we were to take a look at the Sun, for example, let's say there's a star the size of the Sun, and we place that star at a distance of 1 parsec, which is 3.26 light years. Now, there's no star that close to us. The closest star to us is, of course, Alpha Centauri, which is about 4.3 light years. So if we take a star like the Sun, and we move it just 1 parsec away, which is closer than the closest star, the angular size of the Sun would be 0.0093 arc seconds, and that's a very difficult measurement to make. And so the Sun is not a small star, and putting it that close, it still is a very, very small object. So measuring the physical size of a star is very difficult to do. And ultimately, what we're interested in is we want to know the diameter of the star, so we can then find the radius, which is, of course, half the diameter. So how do we do that? Well, there's a number of methods. 3 of the more common methods are what we call interferometry, making direct measurements like that, but with more than one telescope at the same time, so we can make as accurate a measurement as possible. Sometimes we use what we call lunar occultations. When something goes behind the moon, we measure the amount of time it takes for it to disappear behind the moon, and we sometimes can figure out the size from that. Or we use what we call eclipsing binaries, which is usually really the best way to do that. In a lot of cases, stars exist in 2 or 3 groups of 2 or 3, which we call binary stars. So whenever there's more than one star in a solar system grouped together, where one circles around the other, or they both circle around the center mass of each other, we can then say there's a binary star system. And if the line of the star system is in such a way that when they pass one another, they're in the direct view from us to the stars, then they will occult one another. One will cover up the other. For example, the small of the stars sometimes will go in front of the big star, and sometimes will go behind the big star as it goes around like this. Which means we can actually watch it disappear behind the star, and slowly over time the star will move behind like that, and we can measure the time that it takes for it to do so. At the same time, and when it comes over on the other side, it'll start reappearing again, so we have what we call a light curve that changes. When both stars are visible, the intensity and the luminosity of both stars will be at a certain level. once a small star begins to disappear behind the big star, the total luminosity will drop until you only see the luminosity of the big star, which is less than the luminosity of both stars together. And then when the star begins to reappear on the other side, the luminosity begins to increase again and goes back to where it was before. If we can measure the star's velocity, the radial velocity, so we watch it over time, and day after day after day, we watch it move through the sky, and we can then figure out how fast the star moves as it goes around. Another way we can use to measure is as it's moving in a direction away from us and towards us, it's either redshifted or blue shifted, and by using the equation as follows, the velocity is equal to the speed of light times the change in the wavelength divided by the original wavelength. We can use this equation to determine the velocity of the small star as it goes around the big star. From that, we then of course know that the distance covered is equal to the velocity times time, and we can measure the time that it takes for the small star to disappear behind the big star. This is called T1, and we can measure the total time it takes from this point to that point, which is T2, and from those two time measurements we can figure out the diameter of the small star and the diameter of the large star by simply multiplying the velocity, which we determine this way, times the time that it took for the small star to disappear, or for the total time of the occultation. So in that way we can actually measure indirectly the diameter of stars, and we've done so for hundreds and hundreds of stars like that. Once we know the diameter of the star, we can then also figure out the luminosity and the temperature independently, and from that we can learn more about each star. But again, finding the stellar radii, the radius of a star, is a very difficult thing to do and takes a lot of painstakingly measurements over time to get that to somewhat of an accurate value. But you can see, it can be done, and we do so, and that's how we determine the radius of a star. Hey, welcome to Lecture Online, and now we're going to explore how we can find the stellar radius in some other way. So here we have the relationship between the luminosity of a star relative to the luminosity of the sun is equal to the radius of the star relative to the radius of the sun, quantity squared, times the temperature of the star divided by the temperature of the sun, quantity to the fourth power. That came out of Stefan Boltzmann's law. And we can solve this equation for the radius. We can actually set up in such a way that if we know the luminosity of a star and we know the temperature of a star relative to the sun, then we can find out the radius of the star relative to the sun. So rather than measuring it directly using telescope and interferometry and occultation or using a binary star system, we can try to find the radius of a star simply by knowing the luminosity and knowing the temperature. So the first thing we're going to do here is, how do we determine the temperature of a star? Well, we use what we call a filter system. Most often used, we use the B and the V filter, B for blue and V for visible light, which means a B filter lets through light at predominantly 445 nanometers and a narrow band around it, and the visible light filter lets through light at 551 nanometers and a narrow band around it. So let's say we look at a star like Sirius, which is a fairly bright, hot star, fairly high temperatures. So we look at the star with a B filter, and we see how bright it appears. And of course, the brighter it is, the smaller the number, because the magnitude, negative means very bright, and positive means not so bright. The bigger the number, the dimmer, the smaller the number, the brighter. So then we look at the light from Sirius with a V filter, and we see how bright it appears through that filter, and then we subtract the magnitude of the one minus the magnitude of the other. So we take the brightness factor with a blue filter, and we subtract from that the brightness factor with a visible light filter, and then of course if the number is negative, it appears brighter in the blue than it does in the rest of the visible light spectrum, so therefore it must be a very hot star. But if the visible light is a smaller number, that means it looks brighter in visible light, so therefore we get a positive number there. Yes, it's a little bit confusing, but basically what it means, and here we have a table, is the smaller number into the negative, the hotter the star, the bigger number and into the positive, the cooler the star. So in this case, when we do the B minus V calculation for Sirius, we get 0.009, very close to 0. So we go back to our table here and we'll look and we see at 0, the temperature of the star is 9,500 Kelvin, and so it's slightly bigger than 0. So look from 0 to 0.15. It's about 1/15 away from 0 to 0.15, so it's about 1/15 away from this to this. So we can say that the temperature of Sirius, the surface temperature, is about 9,400 degrees Kelvin. So 9,400 Kelvin would be the temperature of Sirius based upon the measurements we made with the blue filter and the visible light filter. So again, notice that the more visible it is through a filter, the smaller the magnitude number, and so therefore a small number minus a big number would give us a negative number, which means that it's not very visible in the visible light, but very visible in the blue light, then we'd get a negative number, very hot star. But if it's very visible in the visible light and not very visible in the blue light, then we would get a very small number here, because magnitude, smaller is bigger. And so a big number minus a small number gives us a big number. That means it's not very hot, it's a relatively cool star. And that's how the B minus V calculation works. So now that we know that, we have one piece of the puzzle in figuring out the radius of a star. We need to know the temperature and the luminosity. The temperature can be measured by looking at the star with two different filters, the blue filter, the visible light filter. We subtract the one measurement from the other as far as the magnitude is concerned, and then we go look on the table to see how hot that star is on the surface. So now we have that. The next portion is to find out how to find the luminosity in an independent fashion, and that we'll see on the next video on how to do that. Okay, welcome to our lecture online. Here we were in the process of determining the radius of a star, and we could take what we call Stefan Boltzmann's law and convert it in such a way that we can calculate the luminosity in terms of the radius and the temperature, or we can rearrange the equation and calculate the radius of a star in terms of the luminosity and the temperature. In the previous video, we saw how using a blue visible light filter, or a blue filter and a visible light filter combined to come up with the surface temperature of a star, and then reading it off the table. And so in our example, we used Sirius, and we knew that B minus Z was equal to 0.009. We looked up the temperature on the table, and we determined that the surface temperature of Sirius is about 9,400 Kelvin based upon taking light measurements with the blue filter and the visible light filter. So we already had one part of the equation. We already knew what the temperature was relative to the temperature of the sun. Now we need to find out the luminosity of Sirius. So the second part of the equation is determining the luminosity of the star, and that is a lot more difficult to do because we know what the luminosity is of Sirius based upon where it's located. We know the apparent luminosity, we know the apparent brightness, but we need to find the absolute luminosity. And how do we do that? Well, the way we do that is as follows. First of all, we need to find what the distance is to Sirius. And to find the distance, since Sirius is close enough, we can use the parallax angle. We can measure the angle of parallax. When we do that, we get the angle to be 379.21 milliarc seconds. So then to find the distance, it's 1 divided by the angle of parallax in arc seconds, and that gives us the distance in parsecs. So let's do that. So the distance to Sirius is 1 divided by 0.37921, because we have to convert to arc seconds. And so when we do that, we get 1 divided by 0.37921, and we get a distance of 2.637, so 2.637 parsecs. And since it's 3.26 light years per parsec, that's time 3.26, that is equal to about 8.6 light years, 8.6 light years to the star Sirius. So divide by 3.26 because I want to keep it in terms of parsecs. Now, what would the luminosity or intensity of the star be when we place that star at the distance of 10 parsecs? Because that's the standard distance for stars to figure out the luminosity. So what we do is we take the distance to where the star actually is and divide that by the distance it would be if we place it at 10 parsecs. We take that number squared because we know the intensity is proportional to the distance squared, and that will give us the change in the intensity. If we then take Sirius where it is now and place it at a distance of 10 parsecs, it would look dimmer to us at a farther distance. We want to know how much dimmer, and we can calculate that here. So this would be equal to the distance that it actually is, which is 2.637 parsecs, and we divide it by 10 parsecs, which is the distance we're going to in our imagination, carrier 2. What would the luminosity be when we took Sirius and placed it at a distance of 10 parsecs away? Well, we can figure that out here. So we divide this by 10, and then we square that number, and we get the intensity would now be only 0.06954 times the intensity that it is at its current location. So the intensity would be less than 10%, about 7% of what it is now when we place it 10 parsecs away instead of its current distance of 2.6 parsecs.
Put a square there.
Oh, yes. Yes, I need to put a square there. Thank you. All right. Next, we want to find the absolute magnitude. We know the apparent magnitude. I have it written here somewhere. The apparent magnitude is minus 1.44. It's the brightest star in the sky. What would be its absolute magnitude when placed at a distance 10 parsecs away? So to find that out, we take the number 2.512, raise it to the difference in the magnitudes, and that is equal to the difference in the intensities, or the change in the magnitude would be equal to the natural log of the intensities divided by the natural log of 2.512. So let's do that. So we're going to take the natural log of the change in intensity. So we take the natural log of that, and we divide that by 2.512, take the natural log of that, equals, and we get a change in the magnitude of minus 2.894. Okay, now we got to be careful here because it's actually dimmer. And of course, the change in magnitude as a positive number is dimmer, not a negative number. So we got to be careful here that we know that this is supposed to be dimmer, not brighter. And here, so we can see this better right there. Okay, now, so the absolute magnitude of Sirius at 10 parsecs instead of at the normal distance, 2.6 parsecs, is as follows. So we take the minus 1.44 and subtract from that. That's why we have to subtract, because it's a negative number, make it bigger. So subtract from that a minus 2.894. All right, so that becomes plus, and then subtract from that 1.44, and we get 1.454. So this is 1.454. That is the absolute magnitude of Sirius. So that would be the absolute magnitude or absolute brightness or absolute luminosity in terms of magnitudes if the star Sirius was 10 parsecs away instead of its normal distance of 2.6 parsecs. Now we can find the luminosity. The luminosity is 2.512 times to the exponent the magnitude of the sun at 10 parsecs minus the magnitude of Sirius at 10 parsecs, because now we can compare it to the sun. So therefore this is equal to 2.512 raised to the magnitude of the sun at 10 parsecs is 4.83. So that's the absolute magnitude of the sun minus the absolute magnitude of Sirius, which we determined to be 1.45. We'll just round it off to 2 decimal places like that. So we get 2.512 raised to the 4.83 minus 1.45 exponents. That's 3.38. So let me write that down. So this is equal to 2.512 raised to the 3.38 exponent. And when we do that, we get 22.5. 22.5. So that is the ratio of the luminosity of Sirius to the luminosity of the sun. So how did we have to do that? Again, quick review. In order to compare the luminosity of Sirius and the luminosity of the sun, we had to put both stars at a hypothetical distance of 10 parsecs away. We know that when we put the sun at 10 parsecs away, the luminosity is 4.83. The question is, or I should say the absolute magnitude, which is in tune with what the luminosity would be. If we were to put Sirius at 10 parsecs, what would be its absolute magnitude? Well, we don't know. We know that the apparent magnitude, where it currently is minus 1.44. So what's the absolute magnitude at 10 parsecs? Well, again, what we do is we first find out the distance using the angle of parallax. Once we know the distance, we then see what the change in intensity would be based upon the relative distance of where it's at to where we're going to place it. So the intensity would drop to about 7% of its normal intensity. So what does that mean for a change in magnitude? Well, we have 2.512 to the change in magnitude equals the change in intensity. So we rearrange the equation. The change in magnitude is the natural log of the change in intensity divided by natural log of 2.512. That gives us a change in the magnitude of 2.894. It's going to be dimmer because it's farther away. So to find the absolute magnitude of Sirius, we take its apparent magnitude, subtract from that the change. When we do that, we get an absolute magnitude of 1.454. We then subtract that absolute magnitude of Sirius from the absolute magnitude of the Sun. We use that as the exponent of the number 2.512, which gives us the luminosity of Sirius, because it's going to be brighter at that distance than the Sun relative to the Sun. So the ratio of luminosities is 22.5. Now, in the next video, we're going to take that and show you how to find the radius of Sirius based upon those two findings. That's how we do that. Hey, welcome to Electron Line, and now we are ready to find the radius of the star Sirius based upon what we discovered in the last two videos. In 2 videos ago, we discovered how to find the temperature of a star using the blue and visible light filters. The relationship between those two was we were able to go to a table and figure out the surface temperature of a star. Secondly, we were able to find the ratio of the luminosity of Sirius to the luminosity of the Sun based upon the apparent magnitude, then figure out how far the star was, then figure out the absolute magnitude, and then figure out the luminosity relationship between Sirius and the Sun. It turned out to be 22.5. So that means that the Sirius is 22.5 times as luminous as the Sun. And finally, we're going to use those two numbers to figure out the radius of Sirius compared to the radius of the Sun using those two numbers. So we can say that the radius of Sirius divided by the radius of the Sun, so in terms of radius of the Sun, is equal to the square root of the luminosity of Sirius divided by the luminosity of the Sun divided by the square root of the temperature of Sirius divided by the temperature of the Sun. Not the square root, it's the number squared, the other direction. So we take the quantity temperature of Sirius divided by temperature of the Sun, quantity squared. So in this case, it would be the square root of 22.5 divided by the quantity 9,400, which is the surface temperature of Sirius, divided by 5,800, the surface temperature of the Sun, quantity squared, and let's see what we get. All right, so starting out with the denominator, we have 9,400 divided by 5,800, and we square that, and then we take the inverse of that, because it's in the denominator, and we multiply that times 22.5, take the square root of that, let's go the other way, there we go, and that equals, and it turns out the luminosity, the radius is 1.805, just sure enough, close enough to 1.8 times the radius. So the ratio, the radius of the Sirius divided by the radius of the Sun is about 1.8, so we can say that the radius of Sirius is equal to 1.8 times the radius of the Sun. And that's not an exact number, but close enough for our purpose to see how we do that. So it is sometimes quite involved finding the temperature of a star using blue and visible light filters, and then finding the luminosity of a star based upon its apparent magnitude, and then converting it to absolute magnitude, see what the brightness or the magnitude would be if we place a star at 10 parsecs. We compare that to what it is for the Sun at 10 parsecs, and then use that information to come up with the ratio of the radius of the star to the Sun. It's an involved process, but you can see, at least in this way, how it's through some clever techniques we can actually figure out how big a star actually is. And that's how we do that. Welcome to Electron Line, and now we're going to look at how to determine the mass of a star in a different way. In this case, we're going to look at it in terms of a binary star system. So let's say we have two stars, and this is the mass m1 of the small star, and there's the mass m2 of the big star. And yes, the small star, we always think of the small object revolving around the big object, but really what's happening is that they're both revolving around the center of mass. So let's say this is the center mass of the two star systems. A1 is the distance from the small star to the center mass, and A2 is the distance from the large star to the end mass. And A here is the distance between the two stars, which is what we call the semi-major axis of the orbit of the small star around the big star, and that will always remain the same, unless of course it's an elliptical orbit and there'll be some small changes. What we can say is, based upon the laws of physics and the center mass and the mass of the objects, that A1, the distance from the small star to the center mass, is equal to the total distance A times the ratio of the mass of the other star divided by the sum of the two masses. That makes sense because the larger the other star is, the farther that the small star will be away from the center mass. So that does make sense. Now also we can go to Kepler's third law and we realize that the period of the orbit squared divided by the distance between the two objects cubed is equal to a constant. That was Kepler's third law. And when Newton came along, he actually took the laws of gravity and included the additional constant, the gravitational constant g, and doing some mathematics, he was able to prove that the sum of the two masses is equal to a cubed divided by p squared. And as long as we express the distance between the stars in astronomical units and the period in years, then the answer will come out in solar masses. If we use the original equation from Newton, then of course we have to put mass in kilograms, period in seconds, and A in meters, and then we'll get the same result. That's why we need these other constants there to make that come out. All right, so what we're going to do here is we're going to write this equation slightly different. First, we're going to bring this to the denominator, so we can write this as the total distance between the two divided by the inverse, because if we divide by this number, we have to take the inverse of that. So we have m2 plus m1. I'm going to reverse the 2 right here and divide by m2. So that's the exact same equation, except we took this and put it in the denominator, which means we have to flip it over. Now we can divide m2 into the numerator here. So this can be written as a divided by the quantity 1 plus m1 divided by m2. Like that. So what we're going to do now is we're going to multiply this times this. So now we have a1 times the quantity 1 plus m1 over m2. That equals a. And then if we multiply this through, or actually a better thing to do would be to go ahead and take the a1 and bring it down here. Let's do that next. So now we can say that we have 1 plus m1 over m2 is equal to a divided by a1. And finally, when we bring the 1 across, now we have an equation that tells us that the ratio of m1 divided by m2 is equal to a divided by a1 minus 1. Now, why did we do that? Well, first of all, over here we had an equation that told us that the sum of the two masses in a binary star system is always equal to a cubed divided by p squared. The distance between them cubed in astronomical units divided by the period that the small star takes to go around the large star in years. We also found out that the ratio of the masses, m1 divided by m2, is equal to the total distance between them divided by the distance from the small object, the small star, to the center mass minus 1. Now we have two equations. We have this equation and we have this equation. Together, we should be able to solve for both m1 and m2. This is how astronomers determine the mass of two stars in a binary star system. What they have to do, of course, is they have to measure the distance between the two stars, and that's usually done over years of observations as they see these two stars revolving around the center mass. They determine this distance, then they determine the location of the center mass and how big this distance is right here relative to the total distance. Then they measure how long it takes for them to make one complete orbit, and knowing the distance between the objects, they know the period and they know the distance from there to there, center mass. They can then take those two equations simultaneously and solve for the two masses of the two stars in the binary star system. And that's how we can get fairly accurate measurements of the masses. Again, it all depends upon how accurately we can measure the distance between the two stars, how accurately we measure the distance from the center mass to the small star. Usually we like to take the largest distance because the larger the distance, the easier it is to measure. And then just simply measure how long it takes to make one complete orbit, and then we'll be able to figure out the masses. If you want to know how that's done, in the next video I'll do an example of how to actually calculate the masses of two stars in the binary star system. And that's how we do that. Welcome to Lecture Online. Now that we know the two equations that we can use to determine the mass of two stars in a binary star system, let's do an example. So here we have two stars, a small one and a large one. The distance between them is a, that's the semi-major axis of the orbit. The distance to the center mass for the small one is a1, and the distance to the center mass for the big one is a2. And the two equations are that the ratio of the two masses is equal to the distance between them divided by the distance to the center mass of the small one, minus 1, that's when the small one is on top. And the sum of the two masses must equal a cubed divided by p squared, which came from Kepler's third law and Newton's law of motion, and Newton's law of gravity, I should say. And so let's say in our example that the period is 10 years, that the small star takes 10 years to revolve around the large star, that the distance between the two is 6 astronomical units, and the distance to the center mass for the small star is 4.5 astronomical units, and we're supposed to find the mass of the two stars. So the first thing we're going to do is find the ratio of the two stars. So we know that m1 divided by m2 is equal to a divided by a sub 1 minus 1. And so a is the distance between them, which is 6 astronomical units, divided by the distance for the small star to the center mass, which is 4.5 astronomical units, minus 1. So 6 divided by 4.5, that would be 4/3 minus 1, which 4/3 minus 1 is 1/3. So that means that the ratio of the small mass to the large mass is 1/3, which means the small mass, the small star, has 1/3 the mass of the big star. So we can say that from this, m1 is equal to 1/3 the mass of the large star. Okay, now we go ahead and use that equation. We know that the sum of the two, m1 plus m2, is equal to the distance between them cubed divided by the period between them squared. The distance being 6 astronomical units, which is cubed, divided by the period, which is 10, and that is squared. And of course, we know that the units end up to be solar masses. So the mass will be in terms of the mass of the sun. So this is 216 divided by 100, which is 2.16. So here we know that m1 plus m2 is equal to 2.16. Now we have to solve the two equations simultaneously. So we're going to substitute for m1. We're going to say m1 is 1/3 m2, or we can write that m2 is 3 times m1. That's probably easier to do. So from here we can say that m2 is equal to 3 times m1. And let's substitute that in, right there. Okay, doing that, we have m1 plus m2, which is 3 times m1, is equal to 2.16. So that means that 4 times m1 is equal to 2.16, which means that m1 is equal to, looks like 0. That would be 54. And of course, that would be the mass of the sun. So the units always are going to be in terms of the mass of the sun. So we can say that would be mass of the sun times mass of the sun times the mass of the sun, which means we determine now that the small star is about half the mass, has about half the mass of the sun. So what about the large star? Well, since the large star is 3 times that, we can say that m2 is equal to 3 times the mass of m1, which is 3 times 0.54 times the mass of the sun, which means that's equal to 1.62 times the mass of the sun, and that would be m2. And you can see that with those two equations and some measurements, which may sometimes take years, we can actually figure out the mass of stars in binary star system. So again, since we have all these various ways of determining the mass, and then have the mass-luminosity relationships, and have the Stefan-Boltzmann's law and Wien's law, and we have the filters by which we make measurements, through all the various ways in which we can calculate the luminosity, the mass, and the radius of the stars, we can then put all that information together and come up with fairly reasonable estimates, calculations that give us a fairly good value for the various things such as the radius, the luminosity, and the mass of stars. None of these are going to give you exact values. There's always some errors and some uncertainties in the measurements, but as we get more and more of these things put together, we'll get a better and better idea of the relationship in stars between the luminosity, the mass, and the size. And so this is what it's all about. Over time, we'll get better and better measurements, better idea, and better understanding about the nature of stars. And that's what it's all about. Welcome to our lecture online, and now let's take a final look at the mass-luminosity relationship. To get a better understanding of stars, we begin to realize that if we chart them out in certain ways, we get some very interesting information. So this is relationship to main sequence stars, and we find that if we draw the relationship between the luminosity of the stars and the mass of stars, and we have the vertical axis to be a logarithmic scale, so that each next increment is 10 times the previous one, it turns out that we get nearly a straight line. And now it's not exactly a straight line. There are some changes in the slope here and there a little bit, but the general relationship is there, that we see this straight line relationship between the mass of stars, and of course you can also see here that this is kind of in a logarithmic scale to some extent, and this is also in logarithmic scale. Notice that if this is the sun, we have 1 times the mass of the sun and 1 times the luminosity of the sun right there. But then if we have a star that is 3 times the mass, it is roughly about 100 times the luminosity. If you have a star that's 5 times the mass, it's roughly 1,000 times the luminosity. If you have a star that is 10 times the mass of the sun, it has roughly 10,000 times the luminosity of the sun. On the other side of the scale, when we get down to pretty well the smallest size that stars can be, about 0.1 times the mass of the sun. Remember, the lowest limit is 0.08 times the mass of the sun. The luminosity is about 1/1000th the luminosity of the sun. So a very interesting relationship, and so it gives you some interesting perspective about the luminosity of stars relative to their masses. So it's the very massive stars in the universe that put out a tremendous amount of light. And that's another look at the nature of stars.